Hello, in this lecture we will find the area of the yellow circle. Uh, we have in the drawing semicircle, and the center of the semicircle is at point O, and let's call the center of the yellow circle M, and actually OQ is tangent to the yellow circle at point O, and the second point of contact between the yellow circle and the semicircle is at point P. And we know that the line segment PQ equals to 7 times root 2. So in order to find the area of the yellow circle, we must know the radius of the yellow circle. And the formula of the area of any circle is actually, let's call the area A. The area of any circle equals to pi times r squared. So this is the formula of the area of any circle. The area equals to pi times r squared. So we have to find the radius of the yellow circle in order to find its area. Okay, so let's connect points O and M together by a straight line. So as you can see, actually OM is actually also the radius of the yellow circle. I will call it small r because MO starts from the center of the circle, that is point M, the center of the yellow circle, that is point M, and ends at point O, that is a point on this yellow circle. And that is exactly the definition of the radius of any circle. Any segment line that starts from the center of the circle and ends at any point at the circle is defined as the radius. So M starts from the center of the yellow circle and ends at point O, that is a point on the yellow circle. For that reason, MO is defined as the radius of the yellow circle, and I called it R. Okay? So actually let's connect points M and P together. Now we actually have rule number 1 that states that if two circles touch each other, rule number 1, rule number 1 states that if two circles touch each other, internally or externally, then their point of contact lies on the straight line joining their centers. Okay, now I will read rule number 1 again. Rule number 1 states that if two circles touch each other internally or externally, if two circles touch each other internally or externally, then their point of contact lies on the straight line joining their centers. Okay, so now I will explain rule number 1. So rule number 1 actually states that if two circles touch each other internally or externally, in our case the yellow circle touch the semicircle at point P, then their point of contact, that is to say P is their point of contact, lies on the straight line joining their centers. So actually the rule number 1 states that the line segment that joins the centers of those two circles, that is to say M and O, this segment line MO actually lies on a straight point with point P. That is to say, line PMO is a straight line. Okay, again, if two circles touch each other, in our case internally, then their point of contact, that is to say point P, lies on the straight line joining their centers. Then point P lies on a straight line that joins the centers together, and the line segments that joins the 2 points together is the line segment MO, and rule number 1 states that PMO is actually a straight line. Okay, PMO is a straight line because the line segment MO with the point P creates a straight line. That is actually what rule number 1 states. If two circles touch each other internally or externally, then their point of contact, that is to say point P, lies on the straight line joining their centers. P lies on a straight line with segment MO that joins, with line segment MO that joins their centers together. So PMO is a straight line. Okay, so actually, if PMO is a straight line, then we can say that MP is also the radius of the yellow circle. And actually, OP is the diameter of the yellow circle, because it's equals to 2R. So we can write here that the straight line OP equals to the diameter of the yellow circle. Okay, OP equals to the diameter of the yellow circle. Okay, this is the diameter of the yellow circle. But because of the fact that OP is a straight line, or OMP is a straight line, then we can actually also say that OP also equals to the radius of the semicircle. So I will mark the radius of the semicircle as R, capital R. So actually OP equals to the radius of the semicircle. I will write down that OP equals to the radius of the semicircle. Now I will explain why OP is the, so I marked it as capital R. It is capital R. The radius of the semicircle marked as capital R. Now I will explain why OP is the radius of the semicircle, because it actually starts from the center of the semicircle and ends at point P, that is a point on the semicircle itself. So any segment line that starts from a point of circle and ends at a point on the circle is defined as the radius of the circle. So because of the fact that line OP starts from the center of the semicircle and ends at a point that is on the semicircle itself, is defined as the radius of the semicircle. So capital R equals to the radius of the semicircle. And actually, for the same reason, we can also say that OQ is also equals to the radius of the semicircle. Okay, I will write it down here. OQ equals to the radius of the semicircle. I will mark it as R. OQ also equals to the radius of the semicircle. I will mark it as R for the same reason, because the segment line OQ starts from the center of the semicircle and ends at a point that is on the semicircle itself. For that reason, it is defined as the radius of the semicircle, because it starts from the center of the semicircle and it ends at point Q, that is a point on the semicircle itself. And this is exactly the definition of a radius. So for that reason, OQ is also the radius of the semicircle, and I marked it as capital R. Okay, and now actually we have the relationship between capital R, that is the radius of the semicircle, to small r, that is the radius of the yellow circle. As you can see from the drawing, capital R, I will mark it as equation number 1. Capital R equals to 2 times small r. Okay, will be the equation number 1. Capital R equals to 2 times small r. Because you can see it from the drawing. The diameter, OP is the diameter of the yellow circle. That is to say, OP equals to 2 times small r. But OP is also the radius of the semicircle. So OP equals both to the radius of the semicircle and also to the diameter of the semicircle. For that reason, the radius of the semicircle equals to 2 times r, because the diameter is defined as 2 times the radius. That is to say, the diameter of the yellow circle equals to 2 times small r, and OP equals to the radius of the semicircle. That is to say, OP also equals to capital R. So also, actually capital R is equals to 2 times small r. Okay. Now we actually have second rule that states, we call it rule number 1, rule number 2, rule number 2. Rule number 2 states that in any circle, a radius and the tangent to that radius are perpendicular to each other. So here MO is the radius of the yellow circle, and we also have perpendicular, QA is the perpendicular to the radius. So according to rule number 2, the radius is perpendicular to its tangent. That is to say, angle POQ will be equal to 90 degrees, and also angle, let's say POL, will also be equal to 90 degrees. So this angle is 90 degrees, and this angle will be also 90 degrees. So I will write down rule number 2. So actually rule number 2 states that in any circle, a radius and the tangent to that radius are perpendicular to each other. So now I will read it again. Rule number 2 states that in any circle, a radius and the tangent to that radius are perpendicular to each other. So actually, if we have a radius, let's call it R, and we have a tangent to that radius, let's call it T, then the radius is perpendicular to the tangent. That is to say, this angle equals to 90 degrees, and also this angle equals to 90 degrees. Okay, so in any circle, a radius and the tangent to that radius are perpendicular to each other. So we actually implemented this rule in our circles, because in our circles we have a radius MO and we have a tangent to that radius, that is QO. So according to rule number 2, the radius is perpendicular to the tangent. That is to say, angle POQ equals to 90 degrees, and also angle POL equals to 90 degrees. Okay? So in any circle, a radius and the tangent to that radius are perpendicular to each other. That is to say, this angle is 90 degrees, and also this angle is 90 degrees. Okay, so actually we created here a right triangle because triangle POQ is a right triangle because of the fact that angle POQ equals to 90 degrees. For that reason, triangle POQ is a right triangle. So actually we will implement the Pythagorean theorem in the right triangle POQ. So in the right triangle POQ, we will implement the Pythagorean theorem. The Pythagorean theorem states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, I will read again the Pythagorean theorem. The Pythagorean theorem states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Okay, so actually it is very simple theorem. The Pythagorean theorem states that the square of the hypotenuse, that is to say AC square, equals to the sum of the squares of the perpendiculars, equals to the sum of the squares of the perpendiculars. So the square of the perpendicular AB equals to AB square plus the square of the other perpendicular, that is CB. So it is AB square plus CB square. Or in this right triangle, it is true only in right triangle. So in this right triangle, this triangle is right triangle because angle ABC equals to 90 degrees. So in this right triangle, AC square equals to AB square plus CB square. Okay, so now I will copy the right triangle POQ and I will implement the Pythagorean theorem in the right triangle POQ. Okay. So if we look on the right triangle, POQ, according to the Pythagorean theorem, the square of the hypotenuse, that is to say PQ square, equals to the sum of the squares of the perpendiculars. So it is equal to the sum of the square of the perpendiculars. So the first perpendicular is DQ, so it is DQ square, or OQ, it is OQ square, plus OP square. According to the Pythagorean theorem, that the square of the hypotenuse, that is to say PQ square, equals to the sum of the squares of the perpendiculars, equals to OQ square plus OP square. Okay, now we will put the data in the equation. We know that PQ equals to 7 times root 2, so it is actually 7 times root 2 square equals to OQ square. OQ equals to R, so it is R square plus OP square. OP equals to R, so it is also R square. And actually 7 times root 2 square equals to 49 times 2, because 7 square equals to 49 and root 2 square equals to 2. So in total we have 49 times 2 equals R square plus R square equals to 2 times R square. Now we can divide the equation by 2. Okay, 49 times 2 equals to 2 times R square. We can divide the equation by 2. So we will get that 49 equals to R square, because 2R square divided by 2 equals to R square. Now we take root from both sides of the equation. So the root of R square is R, and the root of 49 is actually equals to 7. Actually, in math we know that for every positive number, to every positive number it has actually 2 roots, a negative root and a positive root. But in this case, because we are trying to find the radius of the semicircle, the only option that we can take into account is only the positive root of 49, not negative 7, because root of radius is always positive, of course, so we can take into account only the positive number. So R, capital R equals to 7 units. Okay, but as you remember, we actually created equation number 1 that states that capital R equals to 2 times small r. Okay, so we write down the first equation. So capital R equals to 2 times small r, but we know that capital R equals to 7, so we can substitute capital R by 7 in the first equation. We will get that 7 equals to 2 times small r. Now we divide the equation by 2 and we will get that small r equals to 3.5 units. That is the radius of the yellow circle, yellow small circle. The radius of the yellow small circle equals to 3.5 units. Okay, now we have the equation of the circle that states that the area of a circle equals to pi times r squared. So we can substitute the value of r by 3.5 units. We will get that the area of the yellow circle equals to pi times 3.5 squared. Okay, and actually the area equals to pi times 3.5 square, and 3.5 square is equal to 12.25. Okay, so the area of the yellow circle equals to pi times 12.25, and actually pi times 12.25 equals to 38.48 units, and that is actually our final answer to the question. Or we can say that the area of the yellow circle equals to 38.48 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the value of the radius of the yellow circle, and in order to find the value of the yellow circle, we have to know the radius of the yellow circle. So we define as the radius MO as r, small r, and then we used actually rule number 1 that states that if two circles touch each other internally or externally, then their point of contact lies on the straight line joining their centers. So if two circles touch each other, that is to say the yellow circle touches the semicircle at point P, so point P is also the point of contact. So rule number 1 states that their point of contact, that is to say point P, lies on the straight line joining their centers. So actually it states that point P lies on the same straight line of the segment line MO, because segment line MO connects their centers M and O together, and the rule number 1 states that PMO is a straight line because point P lies on the straight line of MO. Or, in other words, PMO is a straight line. Okay, so for that reason, if PMO is a straight line, we can say that PO is the radius, is the diameter of the yellow circle, and actually, because of the fact that OP is a straight line, according to rule number 1 that I mentioned now, so because of the fact that OP is a straight line, then OP must be also the radius of the semicircle, because OP, that is a straight line, exits from the center of the semicircle and ends at a point on the semicircle itself, and that is exactly the definition of a radius. So OP must be the radius of the semicircle, and from the same reason also OQ must be the radius of the semicircle, because of the fact that it exits from the center of the semicircle and ends at point Q, that is a point on the semicircle itself. For that reason, OQ is also the radius of the semicircle. So OP is the radius of the semicircle and OQ is the radius of the semicircle, and we know that side PQ of triangle OPQ equals to 7 times root 2, but we have also the second rule that states that in any circle, a radius and the tangent to that radius are perpendicular to each other. So if we have a radius and the tangent to that radius, then they are perpendicular to each other. That is to say, this angle is 90 degrees and also this angle is 90 degrees. So we can implement rule number 2 in our circles, because we have radius MO of the yellow circle and we have tangent to that radius. That is to say, QO is the tangent to the radius of the yellow circle. For that reason, the radius is perpendicular to the tangent, are perpendicular to OQ. That is to say, angle POQ equals to 90 degrees and also angle POL equals to 90 degrees. So if angle POQ equals to 90 degrees, then triangle POQ is a right triangle. And we can implement, and we know that in this right triangle, the perpendicular PO equals to capital R, it is the radius of the semicircle, and also the second perpendicular, that is OQ, also equals to capital R. That is to say, it is the radius of the semicircle, and we know that the hypotenuse of this right triangle equals to 7 times root 2. So we can implement the Pythagorean theorem on the right triangle POQ. So actually, I draw again the right triangle POQ, and as you can see, PO equals to the radius of the semicircle, and also OQ equals to the radius of the semicircle, and the hypotenuse of this right triangle equals to 7 times 2 units. So according to the Pythagorean theorem, the Pythagorean theorem states that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse, that is AC squared, equals to the sum of the squares of the perpendiculars, and the two perpendiculars in this right triangle is AB and BC, so it is equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AB square plus BC square. Okay, so we can implement the Pythagorean theorem in our right triangle, and we can say that the square of the hypotenuse, that is to say PQ square, equals to the sum of the squares of the perpendiculars. That is to say, it equals to PO square plus OP square. Okay? PQ square equals to PO square or OP square plus OQ square. Okay? So actually, we know that PQ equals to 7 times root 2, so we can substitute PQ by 7 times root 2. We know that OQ equals to R. We can substitute OQ by R, and we also know that OP also equals to R, so we can substitute OP by R. So after we substituted OQ and OP by R and PQ by 7 times root 2, we got that 7 times root 2 square equals to R square plus R square, and 7 times root 2 square equals to 49 times 2, and R square plus R square equals to 2 times R square. Then we divided the equation by 2, and we got that R square equals to 49, so we took a root from both sides of the equation, and we got that R equals to 7 units. Capital R, that is the radius of the semicircle, equals to 7 units. But we know, according to equation number 1, that capital R equals to 2 times small r. So we can substitute capital R by 7, and we'll get the 7 equals to 2 times R, and then we'll divide the equation by 2, and we get that small r equals to 3.5 units. And the area of a circle is pi times r squared, so we can substitute r by 3.5, and we will get that the area of the yellow circle equals to pi times 3.5 square, and 3.5 square equals to 12.25, so it is the area of the yellow circle equals to pi times 12 times 25, and pi times 12 times 25, pi times 12.25 equals to 38.48 units. So the area of the yellow small circle equals to 38.48 units. Okay, thank you very much.